Hello, good morning. Can you see my screen?
Yes, sir.
Okay. So, if you remember that in the last class we were talking about the torque speed characteristics of the induction machine, torque speed or torque slip, because as you know that slip, this is the PDF file. The slip is equal to the omega sin minus omega rotor. Hello? Yes. Anything? Omega sin is the synchronous speed minus omega rotor by omega sin. Sin is the synchronous speed. So what we wanted to show in the last class is that the useful portion of the characteristics is here in this part of the the slope with slope negative part, that is the stable part, and that stable part allows us to do lot of simplification in the characteristics. The simplification, if you look at the expression, you can see that what is the simplification I'm referring to. Sorry, a little here. Look at the equation. Look at the circuit. Even if you look at the circuit, circuit is having such values as R1E, X1E, X2, and R2 by S. This is the basic circuit and equivalent circuit of the induction machine, and V1 is the voltage. That suffix E is indicating that these are the Thevenin equivalent quantities. Thevenin equivalent quantities, they are slightly different from the real physical values. Okay. So what I'm trying to make you note it here is that as S tends to 0, S slip is tending to 0. What does it physically mean? Physically, it means that the rotor speed is coming very close to the synchronous speed. Synchronous speed is essentially the supply frequency multiplied by the 2 by P. It is a mechanical representation. You know that if the machine is, we can modify, we can create a difference between supply frequency. I'm talking all frequencies in terms of radian, just to for clarity. So supply frequency and the mechanical frequency. So we can create a difference by the number of by the choice of the number of poles of the machine. So omega S, if I define omega S as the supply frequency in radians per second, I define omega sin as the mechanical, as the speed of rotation of the magnetic field. The magnetic field inside the machine rotates at this speed, right? And it is decided by the number of poles. And in fact, omega sin is less than or equal to omega S, supply frequency. So that you know, this is this pole creates, number of poles creates the change in the speed of the rotation of the magnetic field, and rotor is essentially trying to catch that speed, that synchronous speed. It is rotor is trying to catch the speed, and in the process, you know, induction machine goes very close to the synchronous speed. Okay, even you can look at the characteristics, negative slope, it goes to very close to that speed, but not exactly to the synchronous speed. And the difference is itself called the slip. So that difference slip is essentially how much it is slipping. Its intention is to catch omega sin, because two magnetic fields always want to rotate at the same speed, and so therefore the magnetic field created in the rotor coil would like to go and get synchronized to the synchronous speed, but it cannot, because the moment it synchronizes, the voltage collapses in the rotor, and therefore the current collapses in the rotor, and therefore the magnetic field itself collapses in the rotor. So it creates a balance. It creates a balance, mean in the sense that to some extent it comes as close to the synchronous speed as possible. It means rotor. However, it also creates a voltage inside the rotor coil and a frequency too, and that frequency is the slip frequency. That means the difference omega S minus omega sin. Okay, so that will be the omega sin minus omega rotor. So that is the slip frequency that is created in the rotor coil into P by 2. If we go to the electrical, this difference into P by 2 is the actual electrical frequency of the voltage and current induced in the rotor coil. Okay, so our interest, you can see from these characteristics that as slip is tending towards 0, this portion of this R2 dash by S is very large compared to R1E, compared to X1E, and compared to X2. So the effective equivalent circuit in the zone of our interest is a very simple equivalent circuit. For electric drives application, we don't spend too much time on thinking about what is the magnetizing current, what is the minor drop happening here and there. We don't do that because everything is controlled. So we look at the machine in the essence, and we look at the machines in the zone of our interest, in the zone where actually we would like the machine to operate. And I told you 2 reasons for the machine to operate in that zone. One reason is that it is a stable zone, and even in the stable zone we would like to operate in the low slip zone. Why low slip zone? Because low slip zone would imply that the loss in the rotor copper loss is less, and therefore the efficiency is more. We cannot afford to operate an electromechanical energy converter at low efficiency. So slip low is low loss and high efficiency. So that is the thing I was arriving at. Now let us start from that. So let us see the torque expression then one more time. So torque expression one more time. If I see TD, let's say TD is equal to this one. This one is the torque expression. One more time, let me write V1 is square by by the current. Here I am writing current R1E plus X1E square plus what? R1E plus R1E plus R2 dash by S square, R2 dash by S square, R2 dash by S square into X1E plus X2 dash square. This is I square, right? Here into R2 dash by S is the power divided by, we know that, omega sin, right? So first of all, a few observations even before you go to the approximation. One interesting observation is here that if R2 dash by S is unchanged, then torque TD is unchanged. All other quantities remaining same is unchanged, right? This is a ratio. R2 dash by S is a ratio. So as long as the ratio is unchanged, the torque quantity will not be different. That means I can design a machine with higher resistance and operate at a higher slip, but I will be getting the same amount of torque. A rotor resistance, let us say a machine where rotor resistance is 5 ohm and the rated torque is obtained at, let us say, 5%, I will get the same amount of rated torque if the rotor resistance is 2.5 ohm and at that point if the slip is 2.5%. So this R2 dash by S as a ratio is working on the torque expression. It is not just R2 dash. It is R2 dash by S. That means the slip could be adjusted when the rotor resistance is different to obtain the same amount of torque. Whether that is good or bad is a different issue. Whether changing rotor resistance and operating at low slip is a better thing. In fact, it is a better thing because it is it can be shown that the loss is less, rotor copper loss is less. Okay, the current is same. As long as you are keeping R2 dash by S ratio same, the current is same, but loss is I square R2 dash. So therefore, physical value of R2 dash should matter when we think about the loss, right? Rotor copper loss, rotor copper loss is what? I2 dash, I am taking I2 dash square into R2 dash. And I2 dash is unchanged. I2 dash is unchanged. Changed if R2 dash by S ratio is unchanged. That is true. That is true. But rotor copper loss will be changing because there is additional multiplication by R2 dash. So a machine which has less rotor resistance has no limitation. It will produce the same amount of torque at a lower slip. It simply needs to produce the same amount of torque at lower slip. But it has a better, from the copper loss of point of view, it is better, right? So that those things you must be looking at these expressions and interpreting. You must be interpreting that this is what it simply physically, this is what the feeling it is giving, right? Okay, so even I can, okay, I will come to that later, a little later. Let us take this thing. So let us say the efficiency of the machine. What is the efficiency of the machine? Efficiency of the machine is how much output power you are getting. How much output power you are getting? I2 square into R2 dash by S into 1 minus S is the output power you are getting. And how much input power you are pushing into the machine, which is I2 dash S square. I am talking in the rotor side. So only taking in the rotor side, stator side loss we are neglecting in this. And this I2 dash S square into R2 dash by S. You can look at it from the equivalent circuit. I have ignored the rotor stator portion. So the circuit is now simply here, right? This is the circuit. This is R2 dash and this is R2 dash by S into 1 minus S. This is what is the output. This is what is the mechanical output. So therefore, this is the output power. The current here is I2 dash. This is I2 dash. This is the supply, equivalent supply. Okay, we have ignored the stator drop. That has no big role in this thing. The stator resistance drop, some small, minor difference, but you must understand the essential functioning of the machine. So therefore, you can see that it is efficiency is nothing but 1 minus S. So what does it imply? It implies that better to operate the machine at low slip. Better to operate at low slip for better efficiency, right? That is what we are gathering from this. So therefore, our characteristics is simply in this zone. It is simply in this zone. Not only this zone. The zone that we are interested in is low slip zone. That means here. This is the zone where we will like to machine to operate. It is low slip zone. We won't go beyond a certain value of torque. That is what is called rated slip. This slip is called S rated. Look at that. As far as the machine is concerned, it can develop higher torque. There is no doubt about it. It can develop. But we won't under steady state condition. Steady state condition means when it is continuously, it has to deliver certain, produce some kind of torque and supply power to the mechanical system. Under that condition, we won't be operating in this zone. No, we won't be operating in this zone. We will be operating only in this zone. Okay, this is what will be the rated torque, T rated. This is what is rated slip. This is torque developed torque, TD rated, and this is the, as far as slip is concerned, this characteristics I am drawing with respect to the slip. This is slip is equal to 0, and this is slip is equal to 1, and this is slip is equal to 0. Slip is equal to 0, implying that this speed wise it is omega synchronous speed. That is what it is implying. So we are operating the machine very close to the synchronous speed, right? So right. Okay. Now, so therefore, if we are working at very low sleep, the effective equivalent circuit of the machine is what now? Because all other values are small. R1, E, X1, E are very small. So what is the effective equivalent circuit? Effective equivalent circuit is simply resistive, where this is R2 dash and this is R2 dash by S into 1 minus S, and this is the supply voltage. V that what we wrote is V. I don't know what was the writing, V1, right? V1 equivalent E is now equal to V1E is equal to V1. That is the terminal voltage that I'm giving. Obviously, this is the per phase equivalent circuit. Don't think that it is 415. It is 415 by root 3. Okay, that is the voltage we are giving, and this current, primary current, is equal to I2 dash. Okay, this is the model of the drive, model of the electrical machine when we are using the machine as an electronic drive, right? It is because what is the difference in electronic drive machine operating at Bilga? Because I will be able to adjust this voltage. In the normal conventional machine, I will not be able to adjust the supply voltage. Here, I would have the ability to adjust the supply voltage. And since I am able to apply it like that, I will operate in such a way that machine is operating always in this zone, low sleep zone. I will put this thing in the low sleep zone. Even if I need different speed. Only problem with this thing, please understand what is the problem. Why we need to change the voltage. Okay, for a certain speed range, this would work because we are going from varying speeds from here to here. This is the variation in the speed. But suppose let us give numbers. Let us say omega sin corresponds to 1500 RPM, right? Now, suppose somebody wants to run the conveyor belt or the mechanical system at a speed very close to 750 RPM. So what I mean is that when it was running at 1500 RPM, and let us say it was developing a full load torque at a sleep corresponding to, let us say how much I should say, 4%. Let us say the sleep was 4%. Sleep was 4%. So sleep was 4% implies that the speed was how much? This is the rotor speed. Rotor, I am writing corresponding to, because I am not multiplying by 2 pi. So what will be the rotor speed? Can anybody tell me at 4% sleep what will be the rotor speed? What is the rotor speed? 1440, right? 1 minus 4 into 1 minus S into 1500. So that is equal to 1 minus 0.04 into 1500. So we can see that 1500 into 4 is 60 RPM. So it will drop by 60 RPM. So this will be about 1440 RPM, right? So 1440 RPM up to this, any speed variation I can do. I can vary speed from 1500 to 1440 RPM. And this variation is happening due to variation in the torque. Some torque it will operate this, some torque it will operate here, some torque it will operate here. This is external world. External world, the mechanical system demands this thing. I will just go to the corresponding RPM and let the mechanical system, due to the mechanical torque demand, let the actual rotor speed vary. But you see that this variation is not so significant. I will later tell you even this small variation I can compensate. I can precisely operate it at 1440 RPM. Okay, I can precisely operate. If the requirement is to maintain 1440 RPM, irrespective of the torque requirement, I can do that. let me clarify. If you don't understand this, you don't understand. Point is, first of all, you assume that we are not varying the supply voltage and frequency. And this is the original machine. And with the original supply, we are not varying anything. There is no electronic drives part in it. So then what happens? Then what happens is that due to the variation of the external torque, as the machine characteristics is like this, and you have already chosen a voltage and you have chosen a synchronous speed, that is omega sin, you have chosen corresponding to 1500 rpm. So essentially you are developing a characteristics like this, out of which you do not operate here, and let the torque vary here, only this portion. So when the torque is varying, suppose the machine has initially developed the rated torque is 50 Newton meter. This is corresponding to 50 Newton meter. This is external world demanding from the machine. So our machine is satisfying it. That means this is the load torque. So this is the developed torque, and wherever they are intersecting, that is the operating point. But load torque can vary. The external world, the mechanical system may require different torque, right? So if the mechanical system is, but mechanical system is saying that please don't vary the speed, but only vary the torque, right? See the difficulty. They said, suppose the first initially I have seen that this, in order to give 50 Newton meter, I have to let the actual rotor speed dip by 60 rpm. That is required. Otherwise, how is it possible to develop torque? Induction machine cannot develop torque until and unless there is a gap between synchronous speed and the rotor speed. That is fundamental. You cannot develop torque. Because if there is no gap between these two speeds, then the voltage in the rotor collapses and there is no current and there is no torque. If there is no current, there is no torque. Torque is phi into I. So I, even if phi is there, I is not there, then there is no torque. So in operation, in our lab or where the supply system is not controlled, supply system is frozen in terms of amount of voltage and amount of and the frequency, then external world's demand is catered by dropping the actual speed of the machine. Okay, synchronous speed remains unchanged. So depending upon different torques, if there is another torque level, suppose this is 25 Newton meter, we'll see that now the speed will be how much? Assuming this line is more or less linear, this is showing that it will be linear, straight line. Okay, so in the straight line, it will be dropping by 2%. 2% means it will be dropping by 30 rpm. So that means this 25, the speed will be 1470 rpm. Whereas this speed was 1440 rpm. This is rotor speed, omega rotor, mechanical speed or the rotor speed. Clear? So this is what is happening. This has to be tolerated. If there is no control, what can I do? But I will show you now that we can have a better way when we are doing electric drives. I can give you 25 Newton meter as well. Okay, I can give you 25 Newton meter as well at a speed of 1470 rpm. At a speed of 1470 rpm, I can provide that kind of I can provide 25 Newton meter at 1440 rpm. Okay, I can provide that characteristics I can generate and provide that. How? By simply adjusting the synchronous speed by that amount. Suppose I start with a synchronous speed of, instead of 1500 rpm, if I would have started with a synchronous speed somewhat close to 1470 rpm, right? Then this drop would have been adjusted to 1470 to 1440, because this amount of this thing requires a drop of 30 rpm. So if my synchronous speed itself is adjusted to 1470 rpm, then it will come down to 1440 rpm, but produce a torque of 25 Newton meter. So this is the flexibility that we want to gain. We want to gain the ability to keep the speed precisely constant. I agree that this speed variation is negligible, and most of the cases we don't even feel it, but still it is a variation. This variation from 1470 to 1440 is a variation. or 1440 to 1470 is a variation. So if the process requires a precise control of the speed, however, variation in the torque, process will say, I will vary the torque. It is like loading. It's like your home loading. How many switches, how many bulbs you turn on, or how many fans you turn on, or what amount of air conditioners you run or refrigerator you run. You say that is my choice, but the supply voltage will not dip, right? So here also that analogy is like that. Here also the constraint will be, they will be saying the mechanical speed should be what I want, but I should have the ability, I should have the option of, that means load is saying that I should have the option of varying the demanding different amount of torque from you, from the machine. Mechanical system would ask for it. That means the characteristics should be speed unchanged, torque changing, which in the original form is not possible. So we have to do a kind of control on the torque speed characteristics, okay, such that I can maintain the speed that they want. I can maintain the speed that the system is. Why only this? If they want, suppose they wanted to run it at 750 RPM, you see the difficulty. How do I run at 750 RPM? In the original form, 750 RPM will be coming here, somewhere here, and it is coming in the zone of what is that called? Unstable zone. And also the machine will be, even if it would have been in the stable zone, it would not have been possible because it is a high sleep. High sleep means efficiency is hardly anything. Efficiency is 50%. The whole machine will burn. You can see that the efficiency is dependent upon 1 minus S. So if I want to run it at 750 RPM, it would be almost impossible, right? It is not the way. So that's why conventionally induction machines are constant speed machines. Constant speed machine means the application we are dictating. For such application you use it where you don't need to change the speed. Okay. Otherwise, otherwise, the machine will say, no, this is not acceptable. That's why in the previous class I showed that for the pump application, you need a throttle. That means the burden is going to the throttle, right? From the machine's point of view, the speed is unchanged. Okay, so this is the need of it. I hope many times we talk, but we cannot clarify to the students why we need it. I hope you are getting the need. Need is very let there be flexibility to vary the torque, but let the speed be what the process demands, or the load demands, or the external world demands, or the mechanical system. Machine should not say, no, I cannot give that speed. Okay, and I cannot give the torque. Whatever torque, within the range, within my operating range, within my steady state of my maximum torque or rated torque that I can give, within that range. Maximum torque, maybe don't misunderstand the maximum torque. This is the physical maximum torque that it can produce. But the rated torque implies the torque at which it would like to operate, beyond which it is not thermally viable. Okay, beyond which it is not possible to operate in the steady state. This thing is momentarily, it may go to that torque. Okay, momentarily the machine will undergo some extra thermal loss, but it will overcome, it will recover, provided you have quickly come back to the zone where there is less amount of loss in the machine and the efficiency is better, right? So let me take another page. So how do I do it? So again, I come back to the equation. The equation is now that torque in the zone I wanted to operate. In the zone I wanted to operate, torque developed is equal to what I wrote is, so equivalent circuit is very simple. This is just R2 dash by S, right? So the torque is nothing but V by I square R2 dash by S. This is the power. I square V by R2 dash by S, right? This is the power divided by divided by 1 by omega sin. This is the simplest expression that we will be thinking now, because in the sleep is low. Sleep, we always operate with sleep is very low. So the torque expression now becomes V by R2 dash by S whole square by omega sin. So what I do is I adjust it in a different way. That is V by omega sin square I write, and numerator I put omega sin, okay, and then sorry, this is I square into R2 dash by S power. This is I square, R2 dash is power divided by omega sin is the torque. So into then this R square, okay, so numerator is S square, omega sin I have put this thing, so omega numerator is S square and denominator is S into R2 dash. Okay, R2 dash is numerator. Okay, did I do correctly? Yeah, no, I didn't do correctly. What is that? I am organizing it this way. V by omega sin square, denominator 1 R2 dash S by denominator. So sorry, so okay.
Sir, 1 by R2 dash.
1 by R2 dash. So I will do that. 1 by dash. Right. So this is the torque expression. Okay. So this S square 1 S square comes, cancels. So what I see is that V by omega sin square into S omega sin by R2 dash. Right. So if you look at it, a machine R2 dash once chosen during the operation, it is a constant. It doesn't change. R2 dash is equal to constant. It's a physical constant. What we can adjust from our perspective is that ratio of V by omega sin. This ratio is adjustable. Why it is adjustable? V is after all the terminal voltage. V has to be interpreted now as terminal voltage. Omega sin is nothing but corresponds to omega supply, because it is nothing but omega supply into 2 by P. So P is number of poles and pole is a frozen thing. So it is also adjustable. SUPPLY. This is also adjustable. This is the adjustable thing. This is adjustable. Right? So what is the thing? If we now go to a different frequency, if we have to go to a different frequency and produce the same amount of torque, by looking at the expression, what is your idea? The idea would be that V by omega sin as a ratio we should not change. Don't change this ratio, right? Because then it is immaterial what synchronous speed you are operating. It is immaterial. This part at least is immaterial, and this part is physically indicating the flux, because V is equal to 4.44 F flux, number of turns, etc. So that frequency part that you take out, that is what then it implies. It physically it is implying a flux quantity, and that you are not changing. But you don't have to understand that at this moment. You simply look at this as an equation, and in the equation you are saying I will change omega sin in such a way that V by omega sin remains constant, right? So that part of the equation is also not within our consideration. Then R2 dash is equal to constant, right? I have changed omega sin. So it has gone to a different omega sin, right? While changing the omega sin, I have changed V in such a way V by omega sin is constant. So I have no way degraded the torque part. If initially this was the omega sin of 1500 RPM, and by going to 750 RPM, as long as I have maintained the voltage by omega sin constant, that means suppose 1500 RPM the V was 415 volt, and when I went to omega sin of 750 RPM, if I have changed the voltage, applied the voltage of 415 by 2, then V by omega sin ratio as a ratio, it is unchanged. So I have not degraded the torque producing ability of the machine. Okay, resistance is a constant, right? Now, as long as I maintain S by omega sin constant, okay, then I am getting the same amount of torque, right? There is no doubt about it. Are you getting what I am saying? The strategy is that change omega sin, both of them will change, but the ratio you keep it constant. Okay, so that part of the equation is going out. Resistance is going out. So torque developed is simply proportional to S into omega sin. And omega sin you can afford to change. What is the consequent small difference it will make? You, in order to get the original torque, you have to probably change slip a little bit, not heavily, a little bit, because the original S omega sin quantity itself, we have seen that earlier example, it was how much? 60 RPM, right? Let us say you have made a new omega sin. So initially it was S1, omega 1 is equal to 60 RPM. So where S1 is equal to 0.04 and omega sin was corresponding to 1500. Let us say the previous example. Now, to a different, I need to operate the mechanical system at 750 RPM or somewhat close to that. So what I do that is that omega sin, this was 1, omega sin 2, I have chosen 750 RPM. Okay, let us say I have chosen. So I have to produce a new slip S2. It will automatically be produced. S2 into omega sin 2 is equal to 60 RPM. If that happens, then it is happening. So what is S2? S2 is equal to S2 would be how much? Omega sin into 750 corresponds to 60. So S2 is equal to 60 by 750. So 60 by 750 is equal to 0.08. It is equal to 0.08 is the is now the what is that? It was the new slip that will be there. But the drop wise, RPM wise, both the cases it is 60 RPM. So what it means is that the characteristics I have shifted. Suppose the original characteristics was I am drawing only the portion where torque is linear and torque is just a function of slip. That is the thing. The torque is just a function of the slip. That is the original part. This is the original part, characteristics 1, right? It was synchronous speed 1500, and our torque, that torque operating torque was like this. Operating torque was like this. This is the first torque TD, which is, let us say, 50 Newton meter, and actual rotor speed was this. Actual rotor speed was corresponding to omega 1 is equal to 1440 RPM. Now new characteristics has come, which is here. How did I do? I just changed V is equal to V2. Second voltage is 415 by 2 I have applied, and omega sin I have applied equal to 750. Okay, so I have kept the ratio. So my characteristics has now shifted with respect to the new one. Okay, and it is again linear. That is what it is. That is what the torque speed characteristics shows. right? It is again linear, right? It is again a linear characteristics. So therefore, here this is the new characteristics will be there, and the new speed will be this. Okay, the torque characteristics is linear with respect to the slip speed. That same amount of slip speed will produce the same amount of torque. So therefore, this difference is again the same. It is again 60 RPM. Okay, which in your turn will say a new slip of 8%. A new slip of 8%. That will be the new slip. The original slip was 4%. The new slip will be 8%. But the machine, the drop in the speed will be in one case 1500 RPM. In another case will be 750 minus 60 is equal to 710 RPM. So it is basically a proportional. Torque is proportional to slip speed. That is the beauty of that is the way we would like to treat the machine when you are doing speed control. This is possible only with the speed control of the machine. This is the possible only when you can adjust the voltage of the terminal voltage of the machine, and let the machine along with the synchronous speed of the supply or synonymously synchronous speed of the machine, which will produce a different rotor speed. While doing the rotor speed, we are no way reducing the ability of the machine to produce torque. Torque is no way a function of any other thing apart from the slip speed. We have to combine this term. It is not just slip what is important, but slip speed. Slip speed is S omega sin. This product is important. It is not when you are operating with a constant frequency application, you should say that it is a function of slip, because omega sin doesn't change it. Here it is function of slip speed. But here it is function of slip speed, when you have the ability to change the synchronous speed, and while changing the synchronous, you are clever enough to change the supply voltage as well. So with this combination, you will say the machine's torque is proportional to slip speed. That is what is the understanding or the basic philosophy or the core philosophy of operation of the machine. And now any other, if you do not want a variation of the torque to produce any variation in the speed, what do I do? Suppose that the example that I was saying, I will take one page because it will be good. Suppose that example, let me take it a little big way. You only can tell me. This I should not have drawn. No, I should not draw to confuse you. This is not our characteristics. Our characteristics is this. Right. And let us say, let me do a little, okay. Anyway, let us say I am doing a little big way so that it's clear, rather clear. Suppose this was the original operating point. This is the original operating point, point number 1. Okay, it has produced, it is then supplying mechanical system to do its thing, and at that thing time you have given, let us say in the controlled way, 750 RPM is the omega sin you have given, and it has developed that torque at 4% slip. So omega rotor is equal to minus 60. S omega is the same, so minus 60 is how much? 710 RPM it is run. Okay, this is fine. The process, let us say, process is happy. Process wants to run it at 700 RPM. Let us consider that. A process wants to run at 750 RPM, and therefore the drive system has given a speed of synchronous speed of 750 RPM. It has automatically decided that the voltage, corresponding voltage, it should be such that V by omega sin is constant. It has decided all that, it is running. Now the process didn't change the demand for speed. That means it still says that you should run it at omega rotor is equal to 710 RPM. But how I want a torque of how much? I want a torque of half torque. I need a torque that is half. Let us say the second portion is I need a torque that is half. Now you see, if you do not change, this is TD2, this may be TD1 and this may be TD2. See, if you do not change what it is like, if you do not change what? If you do not change the voltage, if you do not change the synchronous speed, you will operate what? You will operate at this point, right? You will operate at this point. And assuming this to be a linear curve, it would be, you would be operating, your speed will go to 700. Difference between this is, 750 minus 60. Sorry. So it will be, why others are not talking? 60. So 60 means 60 implies it is implying that it is 690 RPM. 690 RPM. So now the drop will be how much? 30. So 750 minus 30. How much it will be operating? It will be operating at 720 RPM. Okay, that speed will be equal to omega rotor 2. Okay, omega rotor 1 was 690 RPM when it was delivering a torque TD1, and TD1, let us say, is TD2 is equal to TD1 by 2, right? So it is likely to have a speed change, speed increase from 6. Obviously, the load is less, speed supposed to increase. So 720 RPM. But I still need the machine to operate at 690 RPM. Now tell me, what am I supposed to do? What am I supposed to do now? I need the machine to still operate at 690 RPM. What am I supposed to do? Can anybody suggest? What am I supposed to do? I'm supposed to change the synchronous speed? Yes or no? And how much it should be? Can we estimate how much? Yeah.
Synchronous speed and sleep we have to change.
Sleep we don't change. Sleep happens. Sleep automatically happens. Okay. So I know that sleep, since this is the thing, the sleep will be, sleep is proportional to the torque, right? So sleep speed is proportional to the torque. So this sleep speed, what should be then the sleep speed to produce half the torque? Torque is proportional to sleep speed. Okay, now we have reduced, we have made the torque half. So S omega sin, this product has to be half, right? Right? This product has to be half now. That means S2 into omega sin has to be half than what I need, right? So this one is now transferred to the, so as a product it should be how much? As a product it should be instead of 60 RPM it should be now 30 RPM. Okay, so S2 into omega sin 2 has to be 30 RPM. Just because it has to produce the same, the half the torque, right? However, so what characteristics do we need now? It should be half the torque. The product should be 30 RPM. So where should the characteristics pass now? It should pass now through this line. Sorry. Right? This is the torque line. The characteristics now of the machine should now have to pass through this line. This type of characteristics you have to generate. Where this is 690 RPM, I need 30 RPM, I need this thing, slip speed is S omega has to be balanced. So it has to be 690 plus 30, meaning that we have to produce a 720 RPM as the new synchronous speed. As the new synchronous speed, we have to produce this, which may mean a slightly different slip. In fact, if I want to calculate, so I will say that S2 into 720 is equal to 30. So S2 is 30 by 720, right? 30 divided by 720. So it is sleep is now slightly different. It is 4.166%. 4.166%. In the original characteristics position, it would have produced the half the torque at a sleep of half. At a sleep of half, because it has become if I take 750 rpm, so it would have produced this thing at S1 into 750 is equal to 30. So S1 would have been 30 by 750, 30 divided by 750. So that is 4%. It would have produced at 4%, right? When I need to maintain the rotor speed constant, objective is to keep the rotor omega rotor unchanged at 690 rpm, okay, and produce two different torques, TD1 and TD2, where TD2 is half of TD1. So when I was producing TD1, our sleep was how much our sleep was? It was 60 rpm out of 750 rpm. So when I was producing double that torque, I was getting the sleep as 60 by 750. So that is 60 divided by 750. So that is corresponding to 8%, right? If I don't change the characteristics, but I change the torque, then consequence is that the speed goes to 720 rpm, okay, because it needs to produce a sleep of 4%, okay, right? However, if I now adjust the synchronous speed from 750 rpm to 720 rpm, I need to maintain a sleep of 4.166%, or I don't directly dictate it. I just dictate that S2 into 720 is equal to 30 rpm. That is what I am doing. By how? By changing my synchronous speed. By changing my synchronous, then machine characteristics takes over. By changing my synchronous speed, I just generate a new characteristic. This is the new characteristics I'm doing. And then the machine characteristics is taking over, and it is automatically deciding that at this moment that it requires a sleep of 4.166% to match the torque, which is half the TD1 torque. And in the process, what is the gain? The gain is that your rotor speed doesn't change. So you are slightly adjusting your machine's characteristics, or in the not machine's characteristics, I will say your supply to the machine is such a way adjusted that you create.
कनेक्ट करना पड़ेगा, वो हो जाएगा.
P और C दोनों है.
हाँ.
Hello. Say something. You are having question. Hello.
Sir, it was by mistake.
By mistake. Now, any comment you have?
No,
Did you understand? Did you understand or not? No.
Yes, sir. I understood.
So this is what is the objective of the electric drive, to create parallel torque speed characteristics, to adjust the frequency, to adjust the voltage, such that we can shift the characteristics to the level we want. When you want much lower speed, we can create a characteristics like this. We can choose the synchronous speed, accordingly adjust the supply voltage and create it. Then we will have the rated torque produced at this point. And this slip speed will match the original slip speed. S omega S has to be S into omega sin will be unchanged. This is what is the essence of the operation of this machine. And by the way, you already know that V by omega f is called this whatever I said, V by omega sin is essentially dictating the flux of the machine. Is proportional to the flux of the machine. Because of what reason? Because you know the induced voltage expression is 4.44 F VMSE is the flux level, VMSE into number of turns per phase. This is the expression we use. Okay, so this VM into AC is flux phi or flux. It is equal to F phi m, maximum flux. Okay, this is the maximum flux that is allowable in the machine. So you see V by F. V by F is something like V by omega sin quota. V by F is nothing but just a coefficient of omega sin. So V by F is equal to 4.44 phi m into n phase. So V by F constant implies that you are keeping phi m constant. Okay, so this is the constant flux. You are not changing the flux level of the machine. You are keeping the maximum flux constant over the speed range. Any speed you operate, speed range, you have to adjust the voltage and frequency in such a way that flux level is constant. And when you are keeping the flux level constant, you are creating different parallel characteristics. Okay, and then the machine develops the torque in such a way that torque becomes proportional to the slip speed. Torque doesn't become proportional to the slip. Torque doesn't become proportional to the synchronous speed. Torque becomes proportional to the slip speed. S omega sin. This product is torque is then becomes proportional to. So by adjusting, yes.
Sir, I didn't get that part where you derived that this thing. The torque is proportional to S omega sin in previous slides. The derivations, the equations.
Okay.
Yes, sir. Here, sir.
Why from I should I start? The first equation is okay or not? First tell
No,
me,
sir.
don't impose yourself anything. What I have started is that our S, I am going to a zone when slip is tending to 0. Then all these resistances, inductances are nearly negligible. First equivalent circuit you take the synchronous of the induction machine, and all other resistance, inductance are negligible compared to R2 dash by S. Yes or no?
Yes, sir.
Right? So what is torque? What is the basic mechanical definition? Torque is, we have seen that it is power divided by omega sin. Right? Power is I square R. This is I. V by R2 dash by S is I. So I square into R. Right? That is power. Right?
Yes, sir. Divided by omega. Yes, I got it now.
Divided by omega sin. Then I am doing some manipulation. V by omega sin, I am putting it together so that I can keep it constant. I don't want it to vary. And then I see that I get an expression like this. Okay, so I will vary omega sin. Therefore, S omega sin will be varying. However, I will adjust V by omega sin ratio constant. That means I will vary voltage and omega sin together. Okay, and go to different synchronous speed and close to that. In that zone, I need to be only making S omega sin aspect constant. Okay, so that is why the characteristics are shifting. A new omega sin you go, but you have gone with the constraint imposed on yourself that you have adjusted the voltage also. So when you have adjusted the voltage also, you can see the expression TD is nothing but simply proportional to S omega sin.
Yes, sir. Now got it, sir.
Now got it, right? So this is what is the essential. I repeat, man, people, if you know that, you have known almost 40-50% of the about the principle, the basic principle, the basic philosophy that electric drives control is nothing but torque, where the basic principle of operation is T torque is proportional to S omega sin. This happens because V by omega sin ratio is kept constant. V by omega sin ratio is kept constant. Therefore, the torque is now proportional to S omega sin. And S definition is always that omega sin minus omega rotor divided by omega sin. But the product has to be constant if the same torque you require. Earlier with a different omega sin, if 60 rpm produced Newton 60 rpm, S omega sin product had produced 50 Newton meter torque, then at a different omega sin, at omega sin is equal to 750 rpm also, that 60 rpm the product that new S and new omega sin product has to be 60 rpm in order to produce the same 50 Newton meter torque. That is what the meaning is. Okay, so S will appear to be different, omega sin will appear to be different, but for the same torque you need the same amount thing. This is what will be the closed loop controller will be doing. It will continuously find out what S omega sin I need. Okay, so that way you will be able to go into. We'll do that. We'll go a closed loop system and we'll do that. How this S omega sin is obtained. Okay, so for example, half, when the torque is half, we have to have half, but it will be done through a closed loop system. So that closed loop system will give this speed. It will add that speed to the original omega sin, add or subtract. You may say subtract to the original speed and get the required amount of this thing. Or it will take the rotor speed, add to that S omega sin. So it will use that omega sin as that will be required. That is what is required from the terminal point of view. It will measure the rotor speed, plus add this part, S omega sin part. This will come through a closed loop control, the amount of adjustment that is required. Because there is a closed loop control which has a reference of the rotor speed and is a feedback of the rotor speed. So anything different, these two will be different. And anything different, that will be correspondingly changing the S omega sin part as an output, as a quantity. Don't think that anything, it's just a number. So that number will be playing with it and playing with it. And the moment these two things balances, then you get the required amount of these two things, means the speed reference and speed feedback. If they balance, then they come to, then automatically through a closed loop, you know what S omega sin you require, which is what we are back calculating. We are now back calculating. Okay, torque is this much. I suppose somebody tell me the torque has to be, I will back calculate. I will calculate, oh, now you require 30 rpm. So in order to have 690 rpm, I need 720 rpm as the omega sin. That is how I will do now. But automatic, it has to be done through closed loop control. So closed loop control does it, or through a closed loop control, it decides this thing. And this is a measurement quantity. Omega rotor is a measurement quantity. MEASUREMENT, measurement quantity. Okay, so now we'll discuss this again in the next class. And if you have any question, please feel free to ask. So I am then now closing this.